In this section, we're going to be looking at infinite series. And when we talk about infinite series, you can imagine that we'll be bringing infinity into the game. But more importantly, we're going to be talking about a specific type of infinite series called geometric series. Now, geometric series have kind of two parts to it. We have a geometric sum or a geometric series. Now, a geometric series would look like k equals 0 to infinity, a times r to the n, or k. K is our subscript here. Now, this should look familiar from a previous section where we looked at the terms of a sequence that were made up by the function a times r to the k. Now, the difference here is a geometric sum. I still start with k equals 0, but instead of going up to infinity, I just go up to some value of n or n minus 1. And again, a times r to the k is still my function that produces the terms. Now, this is called a finite sum because I'm going up to a finite number here, and we'll look at a specific example in a second. Now, this is called an infinite sum or an infinite series because I go up to infinity. Now, this one, the geometric series, I have a couple of options. I have that it could converge or it could diverge. And we have rules for whether it converges or diverges. Now, for both of these, whether we're using a geometric sum or a geometric series, I have this value of r and I have this value of a. So let's go ahead and look at those. A is the first term of the series. Now, r is the ratio that you multiply each subsequent term by. So r is the ratio. Now, if we look at this, it's the common quotient. Between successive terms in the sum. Now, the a and the r are the same whether you're looking at a geometric sum or a geometric series. Now, here under geometric series, let's go ahead and talk some more about this. I have rules for convergence. This will converge if the absolute value of r is less than 1, and specifically it will converge to a over 1 minus r. If this condition isn't met, if the absolute value of r is not less than 1, it will diverge otherwise. Now, over here for a geometric sum, I'm actually looking at partial sums as a way that you'd want to think about that. So one example for this would be, I could look at something like k equals 0 to 4, a times r to the k. And notice these all start with a 0 here, so that's going to be an important idea that we'll want to keep in mind. So as we do our count here, I'd start with k equals 0, k equal 1, k equal 2, k equal 3, k equal 4. You might say, oh, there's 4 terms there, but if you count them up, I have 5 terms here. So in this particular case, n is equal to 5, and so up here I have that 5 minus 1. Now, a geometric sum will converge to a times 1 minus r to the n all over 1 minus r. A geometric series will converge right over here to s equal a over 1 minus r. So that's kind of the important things we need to know for a geometric sum and a geometric series before we get started on looking at some of the homework problems. Now, for our first example here, we're going to be looking at a geometric sum. And we know it's a sum because up here, this is not going toward infinity. So if the top number was going toward infinity, then I would know I was a geometric series. But since it's not, it's a geometric sum. Now, we're going to use a shortcut formula for this eventually, but I would like to actually write out the terms and get an idea of what this is actually saying. So I'm starting with k equals 0. And then I'm going to do k equal 1, k equal 2, k equal 3, and k equal 4. So if I plug in k equals 0, I get 8 to the 0. My a in this case is an implied 1. If I plug in k equal 1, I get 8 to the first. K equal 2 is 8 second, 8 to the third, and 8 to the fourth. And then the summation sign means to add all of these up. So that's what this is. This S sub 4, actually in this particular case, this would be S sub n. So this would be 5, because this would be 5 minus 1. And I have 1, 2, 3, 4, 5 terms. So if I add these up, 8 to the 0 is 1. 8 to the first is 8. 8 squared is 64. And then we have, I think I got off track here, 64. So I've got this one, this one, this one. And then I have 8 cubed. So 8 cubed is 512. And then 8 to the fourth is going to be 4,096. And then I go ahead and add these up. So I have 4,096 plus 512 plus 64 plus 8 plus 1. And that gives me 4,681. So that's the correct answer here. Now, could I have used this formula up here though? Could I have used that to make this a little faster? What if this was the first 30 terms? I wouldn't want to do that by hand, even though it's kind of interesting. So I could do this another way. I could say my partial sum is equal to A, and again the A is an implied 1. I'll just write out the generic formula first. So in this particular case, A is 1, and that comes from right here. It's whatever is in front of the ratio, and the ratio here is 8. Okay, and then I have in the denominator 1 minus 8, because r is equal to 8. So here in this case, a is equal to 1, r is equal to 8. And then I need to figure out what n is equal to, because I'm going to need that over here in the exponent. So 1 minus 8 to the n. So let's figure out what that is equal to for this case. So like we were talking over here at the beginning, 4 is my top number, but that comes from 5 minus 1. So n in this particular case is 5, because if I come down here, I have 1, 2, 3, 4, 5 terms. So this would be to the fifth. So plugging in, I get 1 minus 8 to the fifth in the numerator, which would be a negative 32,767. Again, this is S sub 5 if I want to think about it that way. And the denominator would be negative 7. And then when I divide that out, I get S sub 5 is equal to 4,681. So get the same answer either way. I kind of like doing them by hand, but if this was, let's say, k equals 0 to 50, I wouldn't want to do that by hand. I think the shortcut would be a lot easier for me there. So these are kind of fun to work with. And it's always nice to do, like I said, a couple by hand so you get an idea of really what the formulas are doing. So for our next one, we're still doing a geometric sum because we're not going to infinity. So we could write these out, but again, I think it's probably a nicer idea to use that shortcut formula. So we need to identify A, R, and N in this case. A is 1, it's this implied value right here out front. R is 7 over 8, and then N would be the n minus 1 that we're looking at here. So it goes up to 10, so that came from 11 minus 1, so n is equal to 11 here. Because I'm going to end up with 11 terms because I'm starting at 0 and counting up. So I'm looking at S sub 11 is equal to A times the quantity, 1 minus R to the n, all over 1 minus R. Now in this particular case, we know A is 1, we know R is 7/8, and the 7/8 is raised to the 11th. Now it's not just the 7, it's the entire fraction 7/8, so make sure you have parentheses around that, all over 1 minus R, which is 7/8. Okay, so let's go ahead and plug this into a calculator and see what we get back. So when I plug that in, I get 6.15847. And I think in my math lab they're asking us to round this to 4 places. So correct rounding here following those instructions would be 6.1585. So if remember, if we go to 4 places, I look at the one past, and if it's 5 or above, I increase the 4 to a 5. So that's another example of being able to use that formula for a geometric sum. It makes things run a lot quicker. Now for our next one, what we want to keep in mind is it has to be in that form for your geometric series before I can get started. Sometimes I have to rewrite things. Sometimes I need to double check that it's actually starting with the basic indice or the lower indice at k equals 0. Because if it doesn't start there, I'm not going to get the correct answer. So the things we want to look for here is I am starting with k equals 0. I don't just have a k in my exponent though, so I'm going to have to rewrite this. I'm going to go k equals 0 to 20. Now here, this is 21 minus 1, so n is equal to 21. But we'll worry about that here in a second. So 2/3 to the 3k, so that would be the same as 2/3 to the third times 2/3 to the k. Because remember, when you multiply like bases, you add exponents. Oh, actually that's not right. It would be 3 plus k then. So it would be 2/3 quantity cubed, all raised to the k here. So if I rewrote that again, I'd get k equals 0 to 20, and then 2/3 cubed. 2 cubed is 8, 3 cubed is 27, so this is 8 27s to the k now. So that's how I can rewrite this. Now once I rewrite this, I have a is equal to 1. Again, that's this implied 1 right here. R is 8 over 27. And n, we just figured out, was 21 from over here. So I should be able to find this geometric sum by using the formula s sub 21 is equal to a 1 minus r to the n all over 1 minus r. So s sub 21, the 21st partial sum, that means I add up the first 21 terms. This is equal to a, which is 1, 1 minus r, r is 8 over 27, to the 21st, all over 1 minus 8 over 27. Okay, so now we're going to plug this into the calculator, and then we're going to round it correctly. And rounding seems like we're going to 4 decimal places. Now you have to be careful here. When I plug this numerator in, just the numerator by itself, my calculator gave me back a value of 1 because it was rounding it up. So make sure that you're really careful about this. Don't round until you get to the final answer. So I get 1.42105. And again, I'm rounding to 4 places, 1, 2, 3, 4. So this is 5 or above, so that's going to round up. So my 21st partial sum here would be 1.4211 would be my correct answer. Okay, so again, these are they're almost more just like arithmetic practically. You wouldn't want to write out all 21 of these terms though. So let's go ahead and look at a lot more of these examples. Now for this one, it's already in a geometric form, so I really don't need to do any rewrite, but I do need to check, am I starting at 0? And I am. So for this example, a is equal to 1. Again, this is an implied 1 right here. R is equal to a negative 2/3. I need to take the negative with it. And n is equal to 10. I get that from 9 is equal to 10 minus 1. So I'm going to have 10 terms. So n is equal to 10. So when I look at the partial sum, then I'm looking at the 10th partial sum. Again, the formula for that is a times 1 minus r to the n all over 1 minus r. So this is s sub 10 is equal to a, which is 1, 1 minus r, negative 2/3 to the 10th, all over 1 minus a negative 2/3. So it's important that we have everything set up correctly here. For instance, I have minus a negative 2/3 because this is negative right here. So I need to make sure I have that. And also this negative 2/3 has to be in parentheses because I'm raising it to the 10th power. Now one mistake I don't want you to make, down here in the denominator, a negative times a negative is a positive, but up in the numerator I can't say that because this negative is raised to the 10th power and exponents take priority when I'm simplifying these. So be careful how you're working with your arithmetic here. So s sub 10 is equal to, we can shortcut this a little bit. We could go 1 minus negative 2/3 to the 10th, And then down here, a minus and negative is the same as a positive. So that'd be 1 plus 2/3. 3/3 plus 2/3 is 5/3. So this is what I could plug into my calculator. So here for my 10th partial sum, I get S of 10 is equal to 0.589595. So we go out 4 places, 1, 2, 3, 4. And so I go one more past, and this is 5 or more, so this rounds up to a 6. So S of 10 is equal to 0.5896. Now again, be careful how you enter this. If I did this problem and I didn't have the parentheses here, it could change the value depending on whether my exponent was even or odd. So be very careful about that. It can make a big difference. So for the next one that we're looking at, first thing we want to do is make sure that we have a geometric series starting at k equals 0. Here n is going to be 9 because 9 minus 1 is 8. Now this one is finally a little bit different. A in this case is 2. And then my value of r is the ratio pi raised to the k. So if I want to look at the geometric sum, I'm going to have the partial sum of 9, S of 9 is equal to a, 1 minus r to the n all over 1 minus r. So what I do is I just go ahead and plug everything in. A in this case is 2, 1 minus pi to the 9th all over 1 minus pi. So we go ahead and plug that in and evaluate it, and we'll round it to 4 decimal places. So if we look at this and we plug it in this particular case, I get 27,837.31937. Of course, I'm rounding to 4 places, so this value of 7 is 5 or above, so this would round up. And I know I'm talking about rounding a lot, but I've had students with a lot of rounding problems even up into calculus, so make sure you keep an eye on that. So my answer here is, if we were going to round it, would be 3194. So this is rounded. But sometimes your directions will be, what is your exact answer in terms of pi? Then what I would do is I'd enter this, 1 minus pi to the 9th all over 1 minus pi. So this is an exact answer. So it depends on what the instructions are asking for, so make sure you read the instructions pretty carefully. Now this problem, we're working a little bit backward. It says to evaluate the geometric sum, but it doesn't give us what that sum looks like. So I think it would be helpful to work backward. Now if you had your calculator, you could just brute force your way in through this. If we notice, my numerator is always 1. My denominator, when I go from 4 to 8, I double it. 8 to 16, I double it, so I'm going times 2 for each of these. So 32 times 2 would be 1 over 64 would show up. Double that, I'd get 1 over 128. Double 128 and I get 256. So I have 1, 2, 3, 4, 5, 6, 7 terms here. So I think what I would like to do is I would like to try and figure out what this looks like in terms of a sum. So I'm going to start k equals 0 to not to infinity, that'd be a series. So I want to go k equals 0 to 6, because I have 1, 2, 3, 4, 5, 6, 7, but I'm starting at 0. So 0, 1, 2, 3, 4, 5, 6. Now if I do that, my first term is 1/4, so that's my value for a. And then how do I get from 1/4 to 1/8? I multiply it by a half. And so that's my common ratio. Now if you want to, you can go through and plug in k equals 0, 1, 2, 3, 4, 5, 6 to make sure that this creates all of the terms here. Now once I do this, I can pretty clearly see that a is equal to 1/4, r is equal to 1/2, and k is equal to 7. And that's because this is 7 minus 1, and there's 7 terms. So 1, 2, 3, 4, 5, 6, 7 terms. So if I want to look at my partial sum, then that would be S sub 7 is a, 1 minus r to the n all over 1 minus r. Now for this one, when I'm looking at the instructions, it's saying simplify your answer. Type an integer or a fraction. So they don't want a decimal here. They want a fraction answer. So that means we're going to have to do quite a bit of handwork here. And a lot of your calculators will do this too, but it's not nearly as fun and exciting as if you do it by hand to get the right answer. So here a is 1/4. 1 minus r, 1 minus 1/2 to the n, and in this case is 7, all over 1 minus r, which is a half. So I'm going to be able to work my way through this. Now 1 minus 1/2 is a half. When you divide by a fraction, you multiply by the reciprocal. And then I get 1 minus 1 over 2 to the 7th, 2, 4, 8, 16, 32, 64, 128. I get 1 over 128. So again, what happened here is we took this 1 minus 1/2 is a half. When you divide by a fraction of a half, you multiply by the reciprocal, so that popped up over here. So let's continue to simplify this. 2 times 1 is 2, 4 times 1 is 4, so 2/4 is the same as 1/2. So s sub 7 is equal to 1/2. And then common denominator here would be 128, so I'd get 128 minus 1 all over 128. S sub 7 then is 127 all over 256. And that's my sum of those. That's my 7th partial sum, and that's the sum of that geometric sum in this particular case. So understanding what the terms come from is going to be important when you're trying to figure out how to work these problems. Okay, so this one, as we're working through, we're trying to find the geometric series now. So this is a little bit different. I'm not looking at a geometric sum. I'm looking at that geometric series. So series is the important word here. Now, if I can't evaluate the geometric series and find a particular finite sum, then I'd have to say that it diverges. So first of all, I need to rewrite this. So let's go ahead and rewrite. So I get n equals 0 to infinity, so that's why I know it's a geometric series. And then e to the negative 7 to the n. So I need to split this off a little bit. I need to rewrite this so I have a common ratio, that r value. So a in this case is 1, and then e to the negative 7 is 1 over e to the 7th, and then that's raised to the n. So here a is 1. R is 1 over e to the 7th, and n in this case is going to be infinity, but I use a different formula when I'm using a geometric series. The sum of a geometric series is a over 1 minus r. So it makes a difference if it's a geometric sum or a geometric series. So let's go ahead and find that sum. So I have a, which is 1, all over 1 minus r, which is 1 over e to the 7th. So what I want to do is find a common denominator here. So it'd be e to the 7th minus 1 all over e to the 7th. When you divide by a fraction, you multiply by the reciprocal. So this e to the 7 pops up top. And I'm left with e to the 7th all over e to the 7th minus 1. So my partial sum is equal to e to the 7th all over e to the 7th minus 1. Now that minus 1 is not in the exponent, so make sure that you're really clear on how you rewrite that. Now for this particular example, they want an exact answer. So an exact answer means you leave it in fractional form. You don't plug it into your calculator to evaluate it and get a decimal. So for this one, it looks like we need to rewrite as well. Key word here is it's a geometric series. And I'm starting with m equal 2 instead of m equal 0. So I need to compensate for that as well. So there's quite a bit going on here really. So to get started, I would want to rewrite. So when I rewrite, I need to remember that I'm starting with m equal 2 to infinity. And then I have a 3 that's out front, so that's my a. And then I'm left with 1/7 to the m. So this 3 over 7 to the m, I could pull the 3 out and I'm left with 3 times 1 over 7m. But again, I have to put this in a geometric form, so I need that 1/7 quantity to the m to fit that particular value. So a in this case is 3, and r in this case is 1/7. So the formula I want is s equal a over 1 minus r, but this is only true when my indices starts with 0. So I have a couple of options here. There's a couple different ways that we could work this. First of all, if we think about starting with 0, so let's say we go 0 and we go clear up here toward infinity, that would be my partial sum up here. But I'm starting at 2 and I'm going up toward infinity. So I think what I could do is I could look at my partial sum, m equals 0 to infinity of 3 times 1/7 to the m, and then I could just subtract off this piece right here because I have 2, my number is going to be too high unless I subtract that off. So what I could do is I could subtract off 3 times 1/7 to the 0, and I could subtract off 3 times 1/7 to the 1. So I think that that's how I could get my answer here. That's one way I could do it. So let's go ahead and look at what we get here. So for my partial sum, I get a, which is 3 over 1 minus 1/7, minus 3, 1/7 to the 0, anything to the 0 power is 1, 1 times 3 is 3, minus 3/7. Okay, and then I can just work through this. 1 minus 1/7 would be 7/7, minus 1/7 is 6/7, minus 3 minus 3/7. When you divide by a fraction, you multiply by the reciprocal. So this would flip right here. So 7/6 times 3 minus 3 minus 3/7. So lots of arithmetic here. And I do notice that 3 cancels here twice into 6. So now I have 7 over 2 minus 3. I'm going to write that as 3 over 1 minus 3/7. Well, my common denominator here would be 14. So here I'd multiply top and bottom by 7. So I get 49. Top and bottom by 7 minus 21. And here top and bottom by 2, so minus 6. So 49 minus 21 would be 28. 28 minus 6 is 22. So I end up with 22 over 14, but of course that reduces to 11 over 14. Well, in just a second, I think I have a mistake here. Let me catch it. And I think my mistake is right here in this middle term. I'm going to go back and fix this. I should have multiplied this by 14. Okay, by 14 times 14. So that middle term should have been 3 times 14, which is 42. I'll fix that here. Now I'm going to get different numbers here. So 49 minus 42 is 7. 7 minus 6 is 1. So 1/14 is that sum. So it mattered that I didn't start with 0 here. So you have to be very, very careful and always check for that. So we have the same issue with this next one. I'm not starting at 0. But I also have another issue, and it's not written in a geometric series form. So I have a couple things I need to look at here. Now, as I think about rewriting this, my indice is still going to start with 1 for now. And I have to remember I need to subtract off that j equals 0 term at some point. So 12 to the negative 2. And then that would be raised to the j. So this looks like a times r to the n. Let's go ahead and keep simplifying it just a little bit, though. So 12 to the negative 2, so that's 1 over 12 squared to the j. Well, 12 squared is 144. So this is j equal 1 to infinity, 1 over 144 quantity to the j. So again, I want j equal 1 to infinity. My series sum is a over 1 minus r. This is if j equals 0 to infinity. So what I'm going to have to do is I'm going to have to find that and then subtract off the j equals 0 term because I have one term too many in that sum. So this is going to look like s equal a, which is an implied 1. It's an implied 1 because it's in front of here all the way along, over 1 minus r. So 1 minus r, r is 1 over 144. And then I have to subtract off my j equals 0 term. So I would be subtracting off 1 over 144 to the 0. So let's go ahead and simplify this. So S would equal 1 over 144 minus 1 all over 144. Anything to the 0 power is 1. When you divide by a fraction, you multiply by the reciprocal. So this flips right here. And so I end up with 144 all over 144 minus 1 is 143 minus 1. Common denominator here would be 143. So I end up with 144 minus 143 all over 143. So that equals 1 over 143. So this is my exact answer. And again, a lot of times the instructions will be very specific. Type an integer or a simplified fraction. They don't want a decimal here. So this next one is interesting as well. It is a geometric series, so it's important to note that. Now remember, this first term is always my a value. So what I want to do is I want to rewrite this and then find the sum or figure out if it diverges. So I'm going to use an indice of n equals 0 to infinity. A is equal to 1, it's my first term right here. And then I have to figure out what am I multiplying this by. Well, to get from 1 to 5e over 8 pi, that's the same as multiplying by 5e over 8 pi. That's my value of r. Now notice if I do 2 as my power, that'd be 5 squared is 25, e squared, 8 squared is 64, and pi squared, so that works pretty slick. So a is 1, and r is 5e over 8 pi. So my sum is equal to a over 1 minus r. So in this particular case, a is 1 over 1 minus r, so that would be 5e over 8 pi. Now I need to find a common denominator here and get rid of these layered fractions. So in the denominator, that's going to look like 8 pi minus 5e all over 8 pi. Now when you divide by the fraction, you're multiplying by the reciprocal of the fraction. So that would pop up top, 8 pi over 8 pi minus 5e. And so that would be the geometric series. That would be the sum of the geometric series there. Now this is one that we're working backward again. We're given the series and then we're asked to find the sum. We're giving the terms of the series, the partial sum here. So what we want to do is to figure out where this comes from. Well, our first term is always a. So I'm going to go n equals 0 to infinity of a, which is 1/5, times r to the n. Well, what do I multiply 1/5 by to get 3/25? And that would be 3 over 5. So that's going to be my value for r. So a is 1/5, and if you want to plug in some values to verify that, you can. R is equal to 3/5. So my sum here would be a over 1 minus r. So that would be a 1/5 over 1 minus 3/5. So that's 1/5 over 5 minus 3 over 5. 5 minus 3 is 2/5. So this is 1/5 times, when you divide by a fraction, you multiply by the reciprocal. So I'm left with 1/2. So in this particular case, s is equal to 1/2. So these are fun to figure out. These actually these aren't too difficult. We can get into some that are a lot more difficult, but these are pretty interesting and fun to do. Well, this one's pretty interesting, and it's similar to a problem we did in one of the earlier sections, but not quite the same. So for this one, it says suppose that you take 200 milligrams of an antibiotic every 8 hours. Okay, the half-life of the drug is 8 hours. So in 8 hours, half is left. So if you take 200 milligrams, in 8 hours, you have 100 milligrams left in your system. And again, that's before you take another dose. It says to use infinite series to find the long-term steady state amount of antibiotic in your blood exactly. So that means we don't want a decimal here. So let's think about a couple things here to get started. Let's think about our first dose. So we start out with our first dose, and our first dose is 200 milligrams. So that this is at hour 0. Okay, so at hour 8, that's when the half-life occurs. I have 200 times 0.5 then is what's left in 8 hours. And in 16 hours, I have half of what was left at 8 hours. So you're going to kind of get the idea here. And in 24 hours, I have 200 times 0.5 times 0.5 times 0.5. So you can see that this is just going to equal geometric series. So this is 200, 200 times 0.5 to the first, 200 times 0.5 squared, 200 times 0.5 cubed. And then this would continue until there's negligible amounts left. Well, keeping this in mind, this just looks like to me, if I said, you know, the hour that we're looking at, we would have a geometric series where we'd have 200 times 0.5 to the n, and of course n would go from 0 to infinity. Here is what we have. Now that's just for the first dose. Now I would do the exact same thing for the second dose. So for the second dose, at hour 0, I don't have anything. And then at 8 hours after I started my first dose, now I start my second dose. And then at hour 16, I have 200 times 0.5 to the first. Hour 24, I have 200 times 0.5 squared. So at hour 24, if I want to know how much of this medication I have in my system, I would take these two and add them together. So that's what I'm trying to do, is I'm trying to figure out how I can rewrite this in a form where I can eventually use the sum of a geometric series formula. So what this ends up looking like is, if I consider all doses, I'm always going to have my most current dose, and that's going to be the 300. And then the dose that I just took would be 0.5 times 300 before that. And the one I took before that would be 0.5 squared times 300 plus 0.5 cubed times 300, and I think you get the idea. And then this eventually goes up to 0.5 to the n times 300. So I should be able to write this in a geometric series. N equals 0 to infinity. A is my first term, 300, and obviously 0.5 is my ratio. So from here, I should be able to put this into the form a over 1 minus r, since I have a geometric series here. So in this particular case, my sum is a over 1 minus r. A is 300, 1 minus r is 0.5. So I get 300 over 0.5, which is 300 over 1/2. When you divide by a fraction, you multiply by the reciprocal. The reciprocal of 1/2 is 2 over 1. So I get S is equal to 600 milligrams is the steady state, meaning I build that up into my blood, and then that's the maximum amount if I keep taking my medication as prescribed. So there's a lot of really interesting applications for these types of series. And this one is another really interesting application. So here what we're looking at is we're given this repeating decimal, and what we want to do is we want to find the fraction that represents this repeating decimal. So for instance, we know that 0.3 repeating is 1/3. So that's what we're trying to find here, is what fraction is this. Well, if we think about 0.4 repeating, the 0.44444, etc., that is equal to 0.4 plus 0.04 plus 0.004 plus 0.0004, etc. So if I look at this in terms of a geometric series, when I move from here to here to my next term, I'm multiplying by 0.1, multiplying by 0.1, multiplying by 0.1. So this A is my first term. So I'm going n equals 0 to infinity, 0.4 times r to the n. Well, the 0.1 is what my common ratio is. That's what I multiply each of my terms by. So A is equal to 0.4, R is equal to 0.1. So the sum, which is going to give me my fraction, is A over 1 minus R. A is 0.4 over 1 minus 0.1. So that would be 0.4 over 0.9, which is 4/9. So 4/9 would be the fraction that could be represented by this 0.4 repeating decimal. And this can be done with more than just the 0.44444. I could be looking at problems, let me see in your problem set. You could have something like 0.063, 0.063. You just have to keep following that pattern to be able to rewrite those out. In fact, let's look at one of those that's a little bit more complicated. So this one we'd set up a similar approach, but instead of the 0.4 plus 0.04, this is going to be a little bit more complicated. This is going to be equal to 0.025 plus 0. Now to get my next one, I need 3 zeros up front, 0, 0, 0, and then I'll have 0.25 plus 0.123456025. So that's what this pattern looks like. So let's see if we can set up a geometric series to match that. It looks like to me that this would look like n equals 0 to infinity. A is my first term, remember. So that'd be 0.025 times r to the n. Well, the question is what do I multiply that by to move this decimal 3 places more to the left? Well, what I would multiply that by is 0.001 because I want to move it 3 places to the left. So 0.001. So in this case, A is equal to 0.025. R is equal to 0.001. So the fraction that I want to find is going to be based on this sum. So I have A over 1 minus R. So my numerator is 0.025, and then my denominator is 1 minus 0.001 would be 0.999. So if I divide, or if I multiply top and bottom by 1,000 to clear my fractions, I get 25 over 999. So if you did 25 divided by 999 on your calculator, you would get this value right there. You'd get the 0.025025. So again, these are kind of fun to do. They're interesting to look at. Okay, let's finish up these last few problems from the homework set that you might come across by looking at, again, the geometric series form and seeing if I can get these rewritten in terms of a geometric series. So this one obviously needs a lot of rewriting. So notice first of all it starts at k equal 1. So I need to keep that in mind because it should be starting with k equals 0 if I want to find the sum. So I'm going to have to find 0 to infinity and then subtract off the 0th term to figure out what this actual sum is. But before I can do that, I need to rewrite it. So let's keep that in mind. I am starting at 1. So negative 7 to the k. So this negative is raised to the k, and so is the 7. So that has to be in parentheses. And then 9 to the k plus 1 would be 9 to the k times 9 to the first. Now, as I rework this, this 9 in the denominator is not raised to the k power, so I'm going to pull that out front. And then this negative 7 over 9 can all be raised to the k. So this is what my series would look like. So in this case, A is 1/9 and R is negative 7/9. Now here I'm going to have to be pretty careful about how I plug that in. I don't want to mess up with my negative and positive values with my fractions. So again, A over 1 minus R, so A over 1 minus R. R in this case is a negative 7/9. And I need to subtract off my 0th term, because remember this would be k equals 0. Well, k equals 0 would be subtracting out 1/9, because negative 7/9 to the k, negative 7/9 to the 0 is 1. 1 times 1/9 is 1/9. So this would be my partial sum. Actually, it would be my sum of my series from 1 to infinity. So this would be 1 plus 7/9, so that would be 9 plus 7 over 9 minus 1/9. So I have 1/9 over 9 plus 7 is 16 over 9 minus 1/9. When you divide by a fraction, you're multiplying by the reciprocal, so this flips up to 9/16. The 9's cancel, and you're left with 1/16 minus 1/9. So here next you would find a common denominator. And the common denominator between 16 and 9 would be 16 times 9. And 16 times 9 is 144. So here I'd multiply top and bottom by 9, top and bottom by 16, and have 9 minus 16 over 144. Final step would be to go ahead and subtract in the numerator. So I get 9 minus 16 is negative 7 over 144. So this sum from 1 to infinity is negative. And that's going to end up happening because this negative is part of my ratio. So the sums don't always have to be positive. Now the last one, actually the second to the last one that we'll do here, these are both geometric series. And so what do I do if I have the sum of two of these geometric series? Well, the answer is you just treat them each individually and then you combine them. And in this case, I'm adding them. You could also subtract, so make sure you keep track of that sign. So for this first one, A is 1/6 and R is 4/7. Second one, A is 2/5 and R is 1/6. So if I want to look at the sum of both of them, it would be 1/6 over 1 minus 4/7 plus 2/5 over 1 minus 1/6. So as we're working here, this would be 1/6 over 7 minus 4 over 7 plus 2/5 over 6 minus 1 over 6. So again, 1/6 all over 7 minus 4 is 3/7 plus 2/5 over 5/6. Now when you divide by a fraction, you multiply by the reciprocal. So it would be 7/3 plus 2/5 times 6/5. So I get 7 over 18 plus 12 over 25. So I'd want a common denominator here. Probably the easiest way to go is just take 18 times 25. I'm pretty sure that's what it would be. So I'd have 7 times 25 plus 12 times 18 all over 18 times 25. So 7 times 25 is going to be 175 plus 12 times 18 is going to be 216 all over 18 times 25 is going to be 450. Now if I add together the numerators, 175 plus 216, I'll get 391 over 450. Now we should probably check to see if that reduces. You could do a factorization on both of those to double check to see what's going on. So let's look at 391 to see if anything is divisible there. Okay, but guess what I forgot to do? You guys probably noticed it right away. I'm starting with k equal 1. So I need to come back and subtract off my k equals 0 for each of my terms, for my first series and the second series. So k equals 0 here, anything to the 0 power is 1, so I'm left with 1/6. And same thing here, anything to the 0 power is 1, so minus 2/5. So I was hoping I'd fit this on a page, but I don't think it's going to happen. So I'm left with 391 over 450 minus 1/6 minus 2/5. So my common denominator I could think about is 450. So if I take 450 and divide it by 6, I get 75. So I'm going to multiply top and bottom by 75. So that's 75 over 450. That's the 1/6 here. And then minus the 2/5. So the 450 divided by 5 is going to be 90. So minus 90 over 450. So it'd be 391 minus 75 minus 90, which would be 226 over 450. Now both of those are even, so this should be pretty easy to reduce. Actually, I think I see a mistake here. So when I did my multiplication here, that should have been 90 times 2 is 180. Okay, and so when I subtract those, then I'm going to get 130, 225, 136 over 450. So let me double check that. Yep, 136, and then when I divide both of these by 2, I'll get 68 over 225. So there you go. So watch out there. So what I did here, remember when you take 450 and divide it by 5, you're multiplying top and bottom by 90, and I just forgot to take 2 times 90 and just wrote the 90. Okay, so I think we have one more problem left that we're going to work, and let's go ahead and pull that one in. Now this last one doesn't look like it's two different geometric series. When I rewrite it, it might look like that. So let's go ahead and first of all, n equals 0, so I am starting at 0 here, so I don't have to worry about subtracting any terms, but I do need to split the numerator. So when I split this up, I have n equal 0 to infinity. I have 4 to the n over 5 to the n minus 1 over 5 to the n. So I can rewrite this, n equals 0 to infinity. I'm going to use a as 1, and then I'll have 4/5 to the n minus 1 times 1/5 to the n. Now for this first one, a is equal to 1, and r is equal to 4/5. And for the second term, and again, this one is subtraction, so make sure you remember that, a is equal to 1, r is equal to 1/5. So if I want to find the sum here, I use my a over 1 minus r. But now remember, this one is subtraction, so then I have my a over 1 minus r. So I have 1 over 5/5 minus 4/5 is 1/5, minus 1 over 5/5 minus 1/5 is 4/5. So this is going to be, when you divide by the fraction, you multiply by the reciprocal. So I have 5 minus 5/4. Common denominator here would be 4. So 5 times 4 is 20 minus 5 over 4, which is 15 over 4. So the sum here would be 15 over 4. So lots of arithmetic on these, and double check your work. I could tell I made a few mistakes. Thankfully I caught them. So as you're working, be careful, keep track of things. Make sure you're using your terms correctly, so make sure that you understand that you should always be starting with 0 for a geometric series, and if you don't, you need to make sure you compensate for that. So as usual, if you have any questions, I'm always happy to help. Just let me know, and good luck. I hope you enjoy working on these.